Hi, I'm Ravindu Nagasinghe from Honglu University of Artificial Intelligence, and I will present our work titled Why Not Use Your Textbook Knowledge Enhanced Procedure Planning of Instructional Videos, which is a procedure planning model that leverages rich procedure knowledge from a probabilistic procedure knowledge graph to assemble a strategic procedure plan. Procedure planning in instructional videos requires an agent to construct a logical sequence of action steps, thereby assembling a strategic procedure plan. This plan is crucial for navigating from an initial visual observation to a target visual outcome as depicted in real-life instructional videos. This task serves as a step towards a future where an agent like a robot can offer real-time assistance, such as help someone prepare a recipe. Procedure planning in instructional videos has been first introduced by DDA that conceptualized the problem as a sequential latent space planning. Here they employ transformers for action prediction while using intermediate visual states for training. Building on this, P3IV view this problem as a distribution fitting problem to mitigate error propagation in sequential decisions. P3IV replaces intermediate visual states with language representations for supervision, predicting all steps simultaneously instead of using autoregressive methods. To circumvent complex learning strategies and high annotation costs of previous work, PDPP models the entire intermediate action sequence distribution using a condition projected diffusion model. But they use task labels as supervision. Skiplan focus on action prediction, breaking down longer sequences into shorter, more manageable subchains by skipping less reliable intermediate actions. In contrast to previous works, our approach does not rely on annotations of intermediate states, natural language step representations, or procedural task labels. Despite the recent improvements in the task of procedure planning, current works face the challenges like the presence of implicit temporal and causal constraint in the sequencing of steps, selecting a viable plan out of all possible plans given initial and goal states, extensive use of annotations to enrich input features or provide supervisory signals, and inability to incorporate the real-life knowledge in task sharing steps. To address these intricacies that previous efforts have overlooked, we need a procedure planning model with minimal supervision that navigate the complexities of step sequencing and its potential variations. We propose KEPP, a knowledge-enhanced procedure planning system for instructional videos that leverages rich procedure knowledge from a probabilistic procedure knowledge graph. By using a knowledge graph, we were able to better navigate the complexities of step sequencing and its potential variations. This approach requires only minimal number of annotations for supervision since it only requires knowledge graph paths and start and goal visual states as inputs, unlike previous methods. We decompose the problem in procedure planning of instructional videos into two sections, as predicting the initial and final steps from the start and end visuals, and then creating a plan using a procedure knowledge retrieved based on these predicted steps. Decomposing prioritize the currently available information and effectively incorporates procedure knowledge, enhancing strategic planning. We report extensive experiments on the 3 datasets under different settings on varying complexity. In the procedure planning, given an initial and a goal state observation, the model is required to plan sequence of action steps A1 to A2 to reach the indicated goal. To this extent, we decompose the problem into two subproblems. The first subproblem is to identify the beginning step A1 and the end step A2. And the second subproblem is to plan the intermediate action steps given the first step and the last step. To tackle the second subproblem, we integrate a probabilistic procedure knowledge graph. Previous studies tackle the challenge of procedure planning in real-life scenarios by extensively harnessing detailed annotations in the datasets to offer supervision signals. In contrast, we propose harnessing probabilistic procedure knowledge graph, which is extracted from the procedure plans in the training set. We use the predicted first step A1 and the last step A2 to retrieve a graph path from the procedure knowledge graph and use the graph paths for conditioned procedure plan. This graph path provides a valuable procedure plan recommendation aligned with the training domain, mitigating the complexity of procedure planning. Relying on training dataset paths, we construct a probabilistic procedure knowledge graph. In KEPP, given start and goal visual states as input, we adapt a conditioned projection diffusion model to identify the first action step and the final step. We refer to this model as the step models. Afterwards, conditioned on this first step and the last step and the planning horizon T, We query the graph to retrieve the relevant graph path from the procedure knowledge graph. Finally, the conditional visual states and the procedure plan recommendations are concatenated to predict the action steps using a condition projected diffusion model we call it as the planning model. For both step model and planning model, we use condition projected diffusion models with different conditions and padding sequences. In the step model to condition the standard denoising diffusion probabilistic model, we concatenate the first and the last visual states along the action feature dimension, which has a length corresponding to the planning horizon. During the denoising process, these conditional visual states can change, potentially misleading the learning process. To prevent this, a condition projection operation is applied, ensuring the visual states and the zero padding dimensions remain unchanged. In the planning model, same approach is used, while keeping the dimensions of the visual state, procedure knowledge graph recommendations, and the zero padding unaltered. The infused procedure knowledge graph is a directed and weighted graph created using the training data. In this structure, each step from the training set is represented as a node, while the edges signifies the likelihood of transitioning from one step to another. This frequency-based graph encapsulates the complexity of step sequencing in procedures and its potential variations, thereby addressing the challenges faced by prior works. To utilize this procedure knowledge, queries are made to the procedure knowledge graph using the first and the last actions predicted by the step model. To find the highest probable path out of all the possible paths, we multiply the probability weights, the edges along the path. Then the top R paths are selected as recommended procedure plans from the probabilistic procedure knowledge graph and are aggregated throughout a linear weighting into a single path and given to the planning model as a condition. We report results for the dataset, cross-task, COIN, and NIV on varying planning horizons for the metrics success rate, mean accuracy, and mean AOU. We require only step class annotations while training compared to prior work. Even though less supervision is used, our model achieves superior results in the most stringent metric success rate in all the planning horizons. Our model that uses two procedure plans slightly outperforms the model that only uses one procedure plan, indicating the potential benefits of incorporating more procedure knowledge from the probabilistic procedure knowledge graph. Our method performs well under the challenging scenario of a long planning horizon. Although our model outperforms most of the prior works in COIN dataset, it doesn't secure the top position when considering small planning horizons. This can be attributed to the fact that the COIN dataset typically consists of only 3.9 actions per video, on average, a scenario where advanced sequential level procedure knowledge is not essential. The advantage of our method becomes increasingly pronounced as the planning horizons expand. Our method's utilization of plan recommendations from probabilistic procedure knowledge graph effectively reduces the complexity of long planning horizons. At the inference time, we provide only initial and goal visual states of the task, where it first readies the first and last steps using step model and use it to query the graph to obtain procedure knowledge graph conditions, which in process are used as condition in the planning model. As reported from the graph conditions, the top path provides the most accurate procedure plan, but by using multiple paths, we can overcome some inaccuracies in the procedure knowledge graph as shown in the task of building a simple floating shelf. Probabilistic procedure knowledge graph improve the performance of our proposed model significantly in all the planning horizons. This indicates the necessity of incorporating real-life everyday knowledge both in task sharing steps and in managing the inherent variability in transition probabilities between steps. Our graph encodes diverse sequencing possibilities for steps, also capturing task sharing steps across the entire training domain. For instance, pour water is a step in the making gelato task, but it can also be a part of the other tasks, leading to a step transition from pour water to add fish. Considering the trend of using LLMs to enhance action anticipation, we compare the accuracies between using procedure knowledge graph conditions and LLM conditions in our model. In examining, it becomes apparent that there are trade-offs between using LLM-generated recommendations and knowledge graph recommendations. For instance, knowledge graph recommendations are constrained by data available in the training set, limiting their applicability to unseen procedural activities. However, considering that the training and testing are conducted on the aforementioned 3 datasets with known activities, knowledge graph recommendations can yield more accurate results compared to LLM-generated recommendations. Our model also exhibited significantly faster training convergence compared to state-of-the-art prior work PDPP. The training efficiency of our method is achieved by leveraging the probabilistic procedure knowledge graph, which provides valuable content that facilitate the model's learning process. To wrap up, We explored the problem of generating procedure plans with minimal supervision, considering causal constraint in the sequencing of steps and the variability inherent in multiple feasible plans. We propose KEPP, a knowledge-enhanced procedure planning system for instructional videos that leverages rich procedure knowledge from probabilistic procedure knowledge graph. Here we infused procedure planning with comprehensive procedure knowledge, which resulted in the developing of a method that requires minimal number of annotations for supervision and delivered superior results on the 3 datasets compared with state-of-the-art models. Thank you.